Hi there and welcome to Avogadro Academy. Now, for today, we have a topic titled Ideal Gas Law in Chemistry. Now, there are several gas laws in chemistry. We have the Boyle's law, we have the Charles law, we have the Avogadro's law, we have the Dalton's law of partial pressure, we have Graham's law of diffusion. For today, we are dealing with ideal gas law. Now, for Boyle's law, we have it stated that the fixed volume of a gas is inversely proportional to the pressure provided that the temperature is constant. That is for Boyle's law. For Charles' law, we have it that the volume of a fixed mass of gas is directly proportional to the temperature, provided that the pressure remains constant. But for ideal gas law, we have it that the product of volume and pressure all divided by the temperature is constant, and that equal volume of all gases at the same temperature and pressure contains the same number of molecules. That is for ideal gas law. We have it once again, let me restate it once again. We have it stated that the products of pressure and volume all divided by temperature is constant, and that equal volume of all gases at the same temperature and pressure contains the same number of molecules. Therefore, we have it from ideal gas law that our PV equal to nRT. This is the ideal gas equation. This is the ideal gas equation. Now, someone might be wondering that how did we get this ideal gas equation? Ideal gas equation is gotten from the combination of three gas laws, namely the Boyle's law, the Charles law, and the Avogadro's law. For Boyle's law, it is stated that the volume of a fixed mass of gas is inversely proportional to the pressure, provided that the temperature is constant. Temperature is constant. For Charles' law, we have it stated that the volume of a fixed mass of gas is directly proportional to the temperature, provided that the pressure is constant. Lastly, for Avogadro's law, we have it stated that equal volume of all gases under the same condition of temperature and pressure contains equal number of molecules, meaning that the volume is directly proportional to the number of moles, provided that temperature and pressure remains constant. So for Avogadro's law, we have it that the volume is directly proportional to number of moles, provided that the pressure and temperature is constant. Now, from the combination of these three laws, we get the ideal gas law. We have it stated that volume is inverse to pressure, that volume is direct to temperature, that volume is direct to number of moles. Volume is inverse to pressure. Volume is direct to temperature. Volume is direct to number of moles. From this one that we're having here, we can have it that our V is inverse to pressure and direct to temperature and number of moles. To eliminate this kind of proportion, we need to introduce constant. So we have our V equal to, now in this case, the constant we introduce is not K, as in the case of Boyle's law, Charles' law, Graham's law of diffusion, but rather the gas constant that we introduce here is R. So we have V equals to R Cn over P, where R is molar gas constant. So we have this. Now, to make this R to stand alone, or in other words, to make it the subject of the formula, we need to cross multiply. So V over 1, we cross multiply, we are going to have this RTN multiplying 1. So we have RTN equal to V times pressure. So divide both sides by temperature and number of mole. So we have this cancels this. So we have our molar gas constant to be equal to the product of volume and pressure, all divided by temperature and number, all divided by the product of temperature and number of moles. So we have this. From here now, we can have it that we can have it here that if we cross multiply, we can have this that nRT equal to PV. We can have this like we have it here. We can have this from the combination of both Boyle's law, Charles' law, and Avogadro's law. Now, from what we are having here, we describe P. We said where P equal to pressure, where P is pressure, and pressure can be measured in millimeter mercury, can be measured in atmosphere, can be measured in torr, can be measured in bar, can be measured in Pascal. So we have this, where V is volume. Can measure volume in dm cube, can measure volume in liters, can measure volume in cm cube. So we have this, where n is number of mole, and it is measured in mol. Now next we have R as the molar gas constant. Depending on the units that it is going to have. I'm going to derive the value for the molar gas constant right now. All right, let's proceed. Temperature is measured where T is temperature, measured in Kelvin. So we have this. So we have this. Now, let me now derive the value for R, which is the molar gas constant. Alright, so we have it that at STP, we have it that our R equal to the volume at STP, the volume of 1 mole of gas at STP is 22.4 dm³. So we have 22.4 multiplied by pressure at STP. Pressure can be 1 atmosphere or pressure can be 760 mmHg. We have them measured also in other units, like in torr, in bar, in Pascal, but the two commonly used units are mmHg and atmosphere. Alright, so here now let's use atmosphere and see what we are going to get. Remember that at STP, one of any gas has a pressure of 1 atmosphere. So we have 1. So pressure here is 1. So let me put the units. We have 22.4 dm³ multiplying 1 atmosphere divided by temperature at STP of a gas has a temperature of 273 Kelvin. So we have 273 Kelvin multiplied by, remember we are dealing with 1 mole of a gas at STP. So we are having our number of mole here is 1. When we divide this, we are going to get our molar gas constant to be equal to, this is 1 mole, When we multiply and divide it, 1 times 22.4 divided by 1 mole times 273 Kelvin, we are going to get 0.082 dm³ atmosphere per Kelvin and per mole. This is our molar gas constant value at STP using the pressure in atmosphere. Alright, what about the value of our molar gas constant at STP if we use our pressure at 760 mmHg? Alright, so our R also equal to 22.4, same value of volume. Our pressure is now 760 mmHg. All over the same temperature, 273 Kelvin multiplied by the same number of mole, which is 1. So we have 1 mole. So our molar gas constant value, when we divide this, we are going to get 62.4 dm³ mmHg per Kelvin per mole. So we are going to have this when our pressure is given at mmHg. So we have this. If our pressure is given at atmosphere, we have this. So we have these values as our molar gas constant. So we have this and we have this. Now let's go into some sub examples to do some calculations on ideal gas law. Alright, example 1 says that calculate the number of moles present in a certain mass of gas occupying 6.5 dm cube at 3 atm and 15 degrees Celsius. And now this question here is a very simple question. As usual in science subjects, if you see any calculation, the first thing to do is to always list out your given parameters. Alright, from the question here, we are given what and what. Number one says that calculate the number of moles. So number of mole is not given. Alright, present in a certain mass of gas occupying 6.5 dm cube. Remember, dm cube is a unit for a parameter which is volume. So we have volume to be equal to 6.5 dm cube. Alright, at 3 atmosphere. We know that 3 atmosphere belongs to pressure. So we have pressure to be equal to 3 atmosphere. 3 atmosphere and 15 degrees Celsius. 15 degrees Celsius. So we have our temperature to be 15 degrees Celsius. Remember, we need to convert this Celsius to Kelvin. So we have 15 plus 273. We are going to get 288 Kelvin. Alright, now let's recall our formula for ideal gas law. We have PV equal to nRT. Alright, we are looking for number of mole. Alright, so what do? We make number of mole to stand alone, or in other words, make it the subject of the formula. And we do that by dividing both sides by RT over RT. So RT cancels RT. So we have our number of mole to be equal to PV over RT. Alright, number of mole equal to, the pressure is what here? 3 atmosphere. The volume is 6.5 dm cube. The molar gas constant is already given as 0.082 multiplied by temperature is 288. So we have 288. When we multiply further, 3 times 6.5, 3 times 6.5, we are going to get 19.5 all over 0.082 times 288, we are going to get 23.616. When we divide further, our number of mole will be equal to 0.83 mole. This is our final answer. So we have this. Remember, I use this value because my pressure is given in the same atmosphere. If I'm giving my pressure in millimeter mercury, I will have to do some conversion here. Alright, let's proceed. Number 2 now. Alright, question 2 now. Question 2 says that a certain mass of gas occupies 5.0 dm cube at 2 atmosphere. So we have our volume to be 5.0 dm cube. Alright, at 2 atmosphere. So we have our pressure to be in 2 atmosphere. Alright, and 10 degrees Celsius. So our temperature is in 10 degrees Celsius. So what do we do here? We convert to Kelvin by adding 273. So we have 10 plus 273, which we are going to get 283 Kelvin. So we have this. What again are we given? Okay, it continues and says that calculate the number of moles present. So number of moles equal to question mark. So we have this. Alright, now let's recall the formula for molar gas constant, which is PV equal to nRT. So we have this. Now, we're looking for number of moles. So what do? Divide both sides again by RT. So we have over RT over RT. So RT cancels RT. So we have our number of moles to be equal to P times V over RT. Alright, so we have number of moles to be equal to, our pressure is 2, volume is 5 over molar gas constant is given as 0.082. So we have 0.082 multiplied by temperature is 283. So we have 283. Alright, when we multiply this, we are going to get 10. We get 10 over, when we multiply this, 0.082 multiplied by 283, we are going to get 23.206. 23.206. Alright, finally, our number of mole equal to, when we divide, we get 0.43 mole as our final answer. So we have this as our final answer. Remember, my pressure is given in what? The atmosphere. So I used my molar gas constant having it in atmosphere. Alright, I'm still going to make a part 2 video on the continuation of this calculation. If you find this video helpful, do well to hit the like button, subscribe, drop a comment in order to support this YouTube channel. Remember, this is Avogadro Academy, where we make science subjects such as biology, mathematics, chemistry, and physics easier for students. Thank you.